Hello, and welcome to the last video for this chapter. In this one, we're talking about proof by contradiction. In this video, we'll understand and apply one more method of proof by contradiction. We'll understand when it's useful to apply this, when the situation calls for it. And finally, we'll talk through a proof that square root of 2 is irrational, and I'll share a little story with you about Hypasus, who was a ancient Greek, one of the Pythagoreans. So I'll tell you a bit about that. All right, let's get started. So proof by contradiction works like this. Let's say we want to prove the statement R. Some statement we want to prove R. One way to do this, and as you know, there's lots of different ways to prove the statement R by now, right? We could do it directly or by contrapositive if it happens to be an implication. Maybe it uses cases, right? We have all these different methods of proof. In this one, we start by giving away the argument. What do I mean by that? I mean, we're going to assume the statement we want to prove is false. That'll be our starting assumption is not R. Now this might seem a little bit weird. If I want to prove R, why would I be assuming that it's false? Well, the idea here is if we assume it's false, and then we can show a contradiction must follow, so some contradiction S, then we can use the laws of logic to conclude that R is true. So how does this work? Well, we're going to start by assuming not R, and then we'll show S, this contradiction has to follow. Remember, a contradiction is false in all cases. So we'll show the implication not R implies S. That's sort of the first step. And then recognizing what we've done here, if we can show that implication, well, since S is a contradiction, not S would be a tautology, right? If S is always false, then the negation of that would always be true. It would be a tautology. So no matter what S is true, or not S is true, hence we showed this first implication, not R implies S. And then we know that not S must be true. This isn't something we have to prove, right? By showing that S is a contradiction, we have not S for free. And so look at what we have here. We have not R implies S and not S. So you should recognize this form. That's modus tollens. So by modus tollens, we can conclude that the hypothesis must be false, right? That is, we must have not R, which we know by double negation is just R. And so that's how that works. Start by assuming not R, so give away the argument. That leads to a contradiction, so we've shown this implication. And then we use the laws of logic and our knowledge of contradictions and tautologies to conclude that our hypothesis, not R, must have been false, and therefore R is true. Before we start looking at an example, I just want to talk through how this applies to a certain kind of statement. Right, so as we talked about, it relies on negating the statement we want to prove. And so what's going to be really important is that you know how to negate statements. This is sort of why we laid all that groundwork in chapter 1 about how to negate an implication, how to negate an or statement or an and statement, right? Using De Morgan's laws, all this good stuff. That's all going to come back here because our first step is going to be to negate the statement we want to prove. So for example, we'll see a few examples like this. If our statement R that we want to prove is a universal statement involving an implication, like for all x and s, p of x implies q of x, then if we identify we want to use a contradiction proof here, our first step would be assuming the opposite of this, would be assuming not R, which is then not for all x and s, p of x implies q of x. And we talked through this in the first video in this chapter, right? Negating universal statements. In this case, that would be an existential statement that would look like this. There exists x and s such that it is not the case that p of x implies q of x. Well, if it's not the case that p of x implies q of x, remember that we can rewrite p of x implies q of x as a disjunction, and then we can negate that. So you might have to look back at that first chapter to remember how to do this. I think that'd be a good idea. But remember, the negation of an implication looks like this. It's the hypothesis is true and the conclusion does not follow. And this would be an existential statement. So we would be assuming, our first step if we were trying to prove a statement like this, would be to assume that there is something such that the hypothesis holds and the conclusion does not follow. So that would be our assumption, and what we would be looking for is some sort of contradiction, right? Saying a statement and its negation are both true, something like that. And that's typically the sort of contradiction we'll get, is that a statement, we don't know exactly which statement, but a statement and its negation are both true. And that's the contradiction we're looking for. So let's look at an example here. So what if we want to prove the statement, the sum of a rational number and an irrational number is irrational? So let's just talk through the proof strategy for something like this one. Notice that written in sentences, there doesn't seem to be an implication here. So why am I talking about implications in the first half of this slide? Well, that's because a lot of these we can rewrite as implications, and that'll be helpful. So if you can do this without my help, try and do this. Try and rewrite this statement, the sum of a rational number and an irrational number is irrational. Try and write that as a universal statement with an implication. Because really, that's what this is. It just takes a bit to see it. So let's go for that. So one way we could do that is to say, for all xy in the real numbers, so for every pair xy of real numbers, if x is rational and y is irrational, then x plus y is irrational. So that's rewriting the original statement. So this statement and this statement are exactly the same thing. I've just expressed it in terms of an implication. And now that we can see it as this sort of form, we have a method for at least starting this, right? We'll start by assuming that existential statement. So what will that look like? Well, our initial assumption is going to be this one, that there exists a pair xy of real numbers such that x is rational, y is irrational. Notice that the hypothesis of my implication up here did not change, right? So that's evidence from how we just negate an implication, right? We get the hypothesis and the negation of the conclusion. And so in the original statement, x plus y is irrational is the conclusion. And so our assumption would be, right, we have the hypothesis, x is rational and y is irrational, and x plus y is rational. So that's the idea here. That will be our first assumption, and we'll hopefully show some contradiction has to follow. So that's our starting assumption. All right, let's try it. All right, let's prove this statement now. Now that we've talked through a bit about how we're going to do it, what the strategy is here. So I'll write proof here. And I'm just going to go ahead and write in parentheses by contradiction. You don't have to do this when you prove something. Let me know which method you're using. Sometimes I'll tell you which method to use, or sometimes as you get better at this, it'll just seem natural that this is the kind of statement we want to use a contradiction on. There might be other ways of doing it, but contradiction lends itself nicely to a statement like this one, especially when we want to show, right, here we want to show a rational number, the sum of a rational number and an irrational number is irrational, but showing something is irrational is hard to do directly, right? We don't know what an arbitrary irrational number looks like. However, we do know what an arbitrary rational number looks like, right? If we can write it as a ratio of two integers, we know it's rational. So, but showing it's irrational is tougher. We have to show it can't be written as a ratio of two integers. That's just a harder problem in itself. And so by assuming that the sum is rational in what we're doing, that's going to give us more leverage. It's all about leverage with these proofs. It's all about taking things that are hard to prove and using a different strategy which allows you to get some leverage on it. That's the idea. So by contradiction, we're proving this, and so our initial assumption is that I'll say assume, I don't need to write a comma there. Assume there exists xy in the real numbers such that x is rational, y is irrational, and x plus y is rational. Remember, we're doing this by contradiction, so we're going to assume that this is rational, this sum. So just like we did with like even and odds, as soon as I have my initial assumption down, now I'm going to start writing things in terms of what I know about an arbitrary element of the set. So like I said at the beginning, y here, we can't really write y as an arbitrary element, using two other constants, because it's irrational and we don't know what irrational numbers look like exactly. Just that they can't be written as ratio of two integers. However, we do know that x is a rational number, and we know that x plus y is a rational number. So here I'm identifying our leverage in the situation. We know how to write x as a rational number. We know how to write x plus y as a rational number, right? We know what those things mean. And so let's start there. We'll sort of not focus on this y being irrational. And that's a little hint to you that maybe this y being irrational is going to be the thing we contradict. Let's see. All right, so we know that x is a rational number, so I'll say since x is a rational number, x is equal to, let's say, a over b, where a and b are both integers, and b is not equal to 0. And then x plus y is also a rational number. So I'll write that line, since x plus y is a rational number, x plus y is equal to, how about c over d, where c and d are integers, and d doesn't equal 0. All right, so now we have our leverage identified, and we've written these out. And now let's put this together. So we know that x plus y is c over d, and we know what x is. So I'm going to rewrite x plus y equals c over d using this other form for x, right? We know x is equal to this, and I also know x plus y equals c over d. So I'm going to use those two bits of information to combine these two equations into one equation. So I'll say x plus y is equal to, rewriting x as a over b, is equal to a over b plus y, but we also know that x plus y is equal to c over d. And so it follows that a over b plus y must equal c over d. Now, doesn't this look strange? Remember that y is irrational. It's not a rational number, but here I have it as, well, it just looks odd, right? It looks like y should be rational based off of this. So let's kind of follow our nose there. Let's solve for y in this. Then y equals c over d minus a over b. So then y, this irrational number, is the difference of two rational numbers. Now, we've already gone through a proof that the sum of two rational numbers must also be rational. Well, the same is true of the difference, but let's go ahead and just prove that last bit. I claim y is a rational number, but let's just do a little bit of algebra and use some logic to really make sure that's totally clear. So I can combine these two fractions, finding a common denominator, so I'll get cb minus ad over bd. And I want to claim this is rational. Well, the top is certainly an integer, since a, b, c, and d are integers, and the bottom is an integer as well. That certainly is not 0, since b and d are not 0. So I'll just write that at the bottom here. Since a, b, c, and D are integers, CB minus AD is an integer, and BD is an integer. And then finally, I'll say since B is not equal to 0 and D is not equal to 0, BD, their product is not equal to 0. Hence, what did I do that all for? Well, that was all just to make sure that this thing, and explain why this thing here is a rational number. Hence, y equal CB minus AD over BD is a rational number. So what's the issue here? The issue here is our assumption was that y was not a rational number, right? Looking up here, y is not a rational number. And down here, it's pretty clear that y is a rational number. And so we have a statement and its negation together, which is a contradiction. So I'll just write here, contradiction. Contradiction. And that's the proof. As soon as I get to a contradiction, I know that my initial assumption must have been false, right? So the negation of that statement must have been false, and hence the statement must be true. And so that's a proof. It's a bit weird, but as you practice more, you'll get more comfortable with it. Let's take a look at another example of a proof by contradiction. Here, the statement we want to prove is, there is no smallest positive rational number. Statements expressed like this as sort of a negative statement, that there does not exist something, that also lends itself nicely to proofs by contradiction, since our assumption would be that there does exist something. And then we have this thing that we can work with and manipulate, and hopefully find some kind of contradiction. Whereas if we tried to show this directly, we would start with the assumption that there isn't, we wouldn't really have any leverage. So, all right, so what might be a good exercise for you if you want, I mean, feel free to do this however you want, but one thing I might find useful is to try and prove this yourself, or at least come up with the initial assumption before I start going through this. So if you want to pause it here, that might be good. All right, so our initial statement, the statement we want to prove is there does not exist a smallest positive rational number. And so the negation of that would be there does exist a smallest positive rational number. So I'll start my proof that way. Proof, and I'll say again, by contradiction. Assume there is a smallest rational number. Another thing that's really useful for proofs is when you have something like this, is to give a name to it. It's sort of one of the simplest things about proofs, but perhaps one of the most powerful is to recognize that we can name things, like just give a variable, assign a variable to it. So assume there is a smallest positive rational number, say R is the smallest positive rational number. So that means any other rational number that exists, R must be smaller than it. So that seems like that's going to be the thing we're going to contradict. We can already see the strategy popping up here is that we're going to try and produce a rational number, maybe based off of R, that is smaller than R. So can you think of such a number? If we know R is rational, a positive rational number. Oh, I didn't say positive here, but it is here. We do need to assume it's positive because there's negative rational numbers, and the notion of smallest doesn't make any sense. Smallest, let me just add a caret, positive rational number. So that's the idea, is we're going to produce a smaller rational number than R. Can you think of a way to do that? consider the number r divided by 2, which is certainly smaller than r. Right? If I take a number and divide it by 2, I'm going to get something smaller. We can sort of take that as a given. If we wanted to prove this, we know r is a positive rational number, so we might do something like, well, we know that r is positive, and so if I multiply it by 2, I'll get something bigger, something strictly bigger. And then what I could do here is sort of divide everything by 2. That would give me 0 less than r over 2 less than r. So we could prove this statement a little bit more, starting with something like this, which maybe is more intuitive or just more obvious. But I think this statement by itself is plenty of obvious. So if I was, say, grading a proof like this, I think this assumption would be fine. I wouldn't be looking for a proof that r over 2 is less than r, unless I specifically asked you to prove something like that. So we're almost done here. What's missing here? Notice I just said consider the number. We do have a smaller number than r. Actually, up here we can see that 0 is less than r over 2. So we have this number that is positive. So all that's left here is to show that r over 2 is rational, and that's pretty obvious. If I take a rational number and divide it by 2, right, if it was expressed as a ratio of 2 integers and I divide it by 2, it'll still be expressed as a ratio of 2 integers, right? So I'm actually going to leave that part of the proof out here. That's something you might want to do, is express r as a ratio of 2 integers, divide it by 2, and show that that's still a ratio of 2 integers. That would be a good exercise. So I'll leave that little step of the proof to the reader. To the reader, r over 2 is rational. Not too hard to prove, but maybe a useful exercise to you to do that. And so if we manage to do that, what we have here is that we have a rational number which is smaller than r. I'll say, but then r over 2 is a positive rational number which is strictly smaller than r. But r is the smallest rational number. And that's a contradiction. Right? If it's the smallest rational number, I shouldn't be able to find a rational number that's smaller than it, but I can, and so that's a contradiction. Hence, and I'll just go ahead and restate it now, hence, there is no smallest positive rational number. Now, I'll say one thing here about generalizing. What if the statement was about real numbers rather than rational numbers? How would I have to change my argument to make that work? Would the statement still be true? Is there no smallest positive real number? That is true. There's no smallest positive real number. And actually, an argument like this, using this divide by 2 thing, so splitting the number in half to get something smaller, that'll totally work. So this proof here can really be kind of co-opted to show that it's true for all real numbers, which would be a stronger statement since that includes rational numbers. I just thought I'd point that out, that that's sort of, yeah, I just felt like I would point that out. Let's take a look at another example. This next example of a proof by contradiction is actually a really important result. So I'll state it as a theorem here. And the result is this, that the real number square root of 2 is irrational. Now this has come up before, right? We actually used this result already to prove some stuff in a previous video. In this video, we'll actually prove it, as promised. Now, before we start proving this, remember that proofs can rely on other theorems, right? Other proofs, other things that have already been shown. And so we're going to need a particular theorem that we've sort of seen before. So in a previous slide, I went through the example that for all natural numbers, if, it's a biconditional statement, so I won't start with if, I'll use if and only if, that n is odd if and only if n squared is odd. So do you remember proving that? If not, maybe you want to go back to that video and take a look at that proof again where we prove this. And then you might actually want to journey back to logic and remember that the biconditional, something like P of n if and only if Q of n, is equivalent to the statement not P of n if and only if not Q of n. So that's really using the contrapositive here, but applying it to a biconditional, is that that'll be the same as this. And so in this case up here, n is odd if and only if n squared is odd. Oops, I meant to write an equivalence and not a biconditional there. N is odd if and only if n squared is odd. Well, that's really saying the same thing as n is even, right, the negation of that, if and only if n squared is even. And so by proving this statement up here, which we did already, we actually get this statement for free because it's equivalent to that. We're going to use this statement in our theorem. We've already proved it, just a bit of a different form, and that'll come up. All right, let's talk about our initial assumption for this. So let's start our proof, and I'll have to mention something along the way. Proof by contradiction. So what'll our assumption be? It's not too hard to negate our original statement. If I'm claiming the real number is irrational, the real number square root of 2 is irrational, then the negation would be that it's not irrational, which is the same thing as saying it's rational. Assume square root of 2 is rational, right? We're giving away the argument to begin with, and we'll show that that can't possibly happen. We get some kind of contradiction. All right, so let me, I guess, start by just writing square root of 2 as a ratio of two integers. So square root of 2 is equal to, let's say m over n, where m and n are integers and n is not equal to 0. Our standard assumption for a rational number. But I'm going to add an extra thing to this, and it's not really assumption, it's something that'll follow from this. So while we could write square root of 2 as m over n, what I want to do, I could also write it a lot of different ways, right? I could also write, if I can write square root of 2 as m over n, I'll say up here, if square root of 2 is m over n, then I could also write it as, say, what, 2m over 2n. That would also work. That's a equivalent fraction, or maybe 3m over 3n. Any integer multiple of m and n would work here as long as I use the same thing on top, because then I can cancel that off. So hopefully you can see why, that's a true statement, that I should be able to do that. But I can actually go the other way. So I'll try and convince you here that I can actually cancel off all the factors between m and n when I write square root of 2. That is, if I want, I could write square root of 2 as m over n, where m and n don't have any common factors. So I'm going to state that here. Square root of 2 equals m over n, and m and n have no common factors. Have no common factors. The idea here being that if they do have common factors, cancel them out and change your m and n to those. And just keep doing that. Eventually we'll get to a point where we've canceled off all the common factors and we'll be left with a fraction in lowest terms. So let me say that here, because some people like to say it like that. That is, the fraction m over n is in lowest terms. So I sort of get this other assumption for free. that m over n is in lowest terms, and that's just based off of this idea of equivalent fractions that I can cancel off common factors until I'm in lowest terms, right? We can do this with a fraction like, 9 over, I don't know, 9 over 27, right? If m was 9 and n was 27, well, I'd cancel off a factor of 3 on top and write this as 3 over 9, and then I'd cancel off another factor of 3 and I'd get 1/3, and then I'd stop. So the thing you have to sort of believe me on here is that no matter what fraction I give you, you can cancel off common factors until you get to a point where they're in lowest terms. So hopefully you can believe that. We could sort of prove it, but I don't know. I think that would be making this a little bit too messy to prove that. I think that's fair enough to assume. So m over n is in lowest terms. Cool. So let's see here. So I have square root of 2 equals m over n. I'd like to, I guess you just kind of got to see it. So what I'm going to do is I'm going to take this equation, square root of 2 equals m over n, and I'm going to square both sides. I'm going to get rid of the square root. Maybe that seems natural for some of you to do. I'll say since square root of 2 is the same thing as m over n, then if I square both sides, 2 is equal to m squared over n squared. And I'm going to go ahead and solve for m squared now. Hence, 2n squared would be m squared. All right, let's see. Can we conclude anything from that? Well, notice that I have m squared written as 2 times some other number, right? So I'll say here, since n squared is rational, since n squared is an integer, right? N was an integer, so n squared is an integer. Since n squared is an integer, it follows that, so m squared is twice an integer, hence it's even, that m squared is even. What can I conclude from this? Well, since m squared is even, this is why I had to do this in the preamble to this proof. N squared is even if and only if n is even if and only if n squared is even. Here we have m squared is even, so it follows that m is even. It follows that m squared is even. Hence, m is even. So that's the part where we're using that previous result. Okay, what do we know about even numbers? We know we can write them as 2 times some integer. Hence, m is even. Let's say m is twice k for some integer k. All right, and now we have m written as 2 times k, so let's go ahead and plug that back up in the equation here. Then we have, so 2n squared is equal to, so plugging 2k in for m, I'll write it out, 2k squared, which is 4 times k squared. And so 2n squared is equal to 4k squared, which implies if I divide by 2 on both sides of that, I get n squared is 2 times k squared. So now look at this, I have n squared written as twice an integer. And so n squared is even. It follows that n is even. Now you might not see it, but we're actually done with the proof. That's our contradiction. So what's our contradiction? We know that n is even, right? We concluded that. And we also, along the way, found that m was even. So n is even and m is even. What does that mean? Since m is even and n is even, I don't need that comma there, but I'm not going to erase it. M is even and n is even. Well, what does that mean? They both have a factor of 2. So they do share a common factor. Since m is even and n is even, they share a common factor. That's a contradiction. We said before that they did not share any common factors, right? So they share a common factor, and up here we started this off by saying, hey, we can take any rational number and write it so that it doesn't have any common factors, and we did that. So we did that. M and N had no common factors, and then we showed that they did have a common factor. That's crazy. That's a contradiction. And so that proves it. It must be, then, that our initial assumption was false. It must be that square root of 2 really was irrational after all. So I gave away the argument and reached a point of nonsense, of a contradiction, and so we have to conclude that our initial assumption was false. And so there you have it. We now know and can explain why and can prove for sure that square root of 2 is irrational. Maybe this doesn't seem super important to you. Maybe it does. But this does have an important sort of historical story that goes along with it. So in this slide, I just want to tell a story. This is the legend of Hypasus, the Pythagorean. I don't know if I'm saying his name 100% correctly, but whatever. It's ancient Greek, so no one really knows how it was pronounced. Hypasus the Pythagorean. So you're undoubtedly familiar with the Pythagorean Theorem, and probably of Pythagoras himself. Sort of the person. Maybe you think the Pythagoras himself came up with the Pythagorean Theorem, and maybe he did. That is a result that's attributed to Pythagoras. But really, there was a whole collection of people that followed Pythagoras, sort of the cult of the Pythagoreans. They were a community of people that lived together. So this is, about Pythagoras of Samos, which is an island in Greece, and the Pythagoreans. So this takes place, about 570 before the Common Era on the Greek island of Samos, where Pythagoras was born. Later on, he moved to this town in Italy, Croton, and started the first community of Pythagoreans. So the Pythagoreans were very interesting folk. They're credited with the following discoveries: the Pythagorean Theorem, of course you're familiar with, the sphericity of the Earth. So they were one of these groups that first proposed that the Earth was round, was spherical, much to the dismay of the populace at that time. They're also credited, I didn't know this when I was going back and research, they're also credited with knowing the 5 regular solids, sometimes called the Platonic solids, after Plato, who gave an argument that there were only 5 of these regular solids. And actually, when I saw that, I started looking more into the connection between Pythagoras and Plato, who hopefully you've heard of before. And apparently Pythagoras had a lot of influence on Plato's thought. And then Plato, had some thought on, imparted some thought on Aristotle, who imparted this on Newton. And so in some way, the whole of calculus and all of Newton did kind of comes back to the Pythagoreans and their way of thought and some things that they proved. Proved or showed or gave arguments for. They're also credited with identifying, right? There was this star that would always come up in the morning and the evening that you could always see. No one knew quite what it was. They just thought it was one of the other stars. And the Pythagoreans, one of the first people to identify that this was actually a planet. This was Venus, a planet in our solar system. And they also started this idea, right? They kind of influenced Copernicus in his idea that maybe the Earth wasn't the center of the universe, right? That maybe that the sun was the center of our solar system. That there's this other idea, right? Again, much to the dismay of the populace at the time. So they did a lot of these really cool early things, including the sphericity of Earth. Maybe we need to get their argument back into play to show some of the flat earthers. At any rate, the Pythagoreans were very interesting. They They held very high regard for music and mathematics. They believed in this form of reincarnation. They were vegetarians. They were kind of a very, I guess you might describe them as a very progressive community. And they did a lot of really, really cool stuff. Anyway, back to Hypasus. Who's this Hypasus guy? Well, the legend goes that one of the things the Pythagoreans believed was that any number that existed could be written as the ratio of two integers. Again, this is a legend, so some scholars kind of don't really believe that. There's all these technical issues to that. But anyway, this is how the story goes. They thought every number was a rational number, essentially. Along comes Hypasus, who used a clever geometric argument to prove that the hypotenuse of a triangle with unit legs, so the length of each leg was 1, and then they looked at the length of the hypotenuse. So if you remember the Pythagorean theorem, right, they're very familiar with this, that would be the square root of 2. And Hypasus was able to show that this hypotenuse, the square root of 2, that length, could not be expressed as a ratio of two integers, that it was impossible to express it this way. And hence, there exists this number, namely the length of this hypotenuse, that was not a ratio of two numbers. And upon sharing his proof with his comrades, they were on a boat at the time, the people that were with him, the other Pythagoreans, were so dismayed by this, that there exists this thing outside of their worldview, that they threw him overboard and killed him. And so that's the story. Prove that the square root of 2 is rational, and what did he get for that? He was killed. It was simply too crazy for them to believe at the time, even though he had this nice proof that it existed. And so that's the story of Hypasus, the Pythagorean, and a little bit about the irrationality of square root of 2. By the way, this is a common theme in mathematics, where a new number like this, square root of 2, is brought up that doesn't fit with the other numbers, right? It's not rational. And people before that were like, well, all numbers are rational, but this one's not. And so that starts, right? It's initially met with a lot of hate against that, right? People are hating on that idea that there is this thing outside of their worldview, like square root of 2 being irrational. Another example of this is later on, when people were very obsessed in Italy with finding roots of polynomials, and in particular roots of cubics. The cubic formula had not been invented, but along came someone, I'm trying to remember who it was, I can't quite remember. Someone came along and said, well, there's this way to get a cubic formula, to always get the roots of a cubic equation, but in order to do so, we need to introduce these numbers that are, they don't really exist, they're imaginary. It's the square root of -1, which we know it makes no sense, but nevertheless, I'm gonna call it something. I'll call it an imaginary number, and that's necessary in order to prove that these roots exist and what the roots are. And it was this really tremendously great idea to use this intermediate step of an imaginary number. And as we all know now, imaginary numbers are really useful for things like electrical engineering. They're all over the place. In physics, they come up all the time, especially in like particle physics and field theory. But at the time, right, people were like, this is nonsense. The square root of 2 the square root of -1 doesn't exist. And so this is along the same themes, that someone will come along and sort of come up with something just so weird, so out of the mainstream, that initially it's met with a lot of anger and issues with that. But then eventually the usefulness of that idea becomes apparent, and it gains popular acceptance. So now imaginary numbers are not so weird. We use them all the time. A lot of our communication equipment and everything relies on these negative numbers. So one thing you might think about, what's the next big idea? All right, that's the end of this.